My name is Sherwin, and in today's series of videos, I'm going to be talking about complex numbers, which are one of the first subjects you learn at uni. I'm going to develop this topic from scratch and cover pretty much everything that you learn in first year for this topic. So this is a sample of the face-to-face uni prep courses we are running at Mathemagical Education. So the thing is that maths is taught much more formally in uni than it is at high school, which is why a lot of students really struggle. So in these courses, we try and help to make the transition for students as easy as possible. So if you're interested, please refer to mathed.com.au, and I hope you enjoyed today's series of videos. So let's get into it. So first, an introduction. So I want to explain where does this idea of complex numbers come from. So as you know, all of our lives we've always been told that the square root of a negative is undefined. So whenever we have a square root, whatever's underneath the square root has to be non-negative. And if you have a negative number underneath the square root, that's pretty much it. Math error, undefined. But what we're going to do now, we're going to do something which seems a little bit crazy and a little bit weird. We're actually going to say, alright, what if we let the square root of a negative number be defined? In particular, we're going to take the square root of negative 1 and we're going to define that to be I. Now obviously this I is not a real number. It does not physically exist. So what we do, we call it an imaginary number, because that's literally what it is. It's an imaginary number. Now, like I said, this may seem like a crazy idea and kind of pointless, but as you will see by the end of this video, it's actually extremely useful. So for one, imaginary numbers are a great means to solve many real problems. So there are many real problems where if you use imaginary numbers, it provides a very efficient and slick means to solve that problem. And in fact, some problems become very difficult or pretty much impossible if you don't use complex numbers. So there's some examples here. So for example, finding the exact value of sine pi on 5, or doing this integral here, right? Both of these problems use the idea of imaginary numbers, but that's just a small sample. By the end of today's video, you'll see many real-world problems that I'll solve quite nicely using imaginary numbers. So that's one thing. Another important thing, although we won't really see it in today's video, is that imaginary numbers give a great way to model 2D phenomena, because if you take the real numbers, which is the numbers we use all the time, and you add the imaginary numbers to that, all of a sudden what you have a two-dimensional system. And you'll see that this two-dimensional system, or the set of complex numbers, is very easy and nice to work with. So a lot of subjects use this setting of complex numbers to model 2D situations, and so complex numbers is used a lot, and it's all over the place in places like fluid dynamics, electrical engineering, signal processing, quantum mechanics, just to name a few. So it's an extremely useful topic, and in fact some of the most beautiful results in all of maths arise from studying imaginary numbers. And we'll see a little bit of that in today's video, hopefully. Okay, so let's talk a little bit about how we should do arithmetic with these imaginary numbers, because so far all we've established is that the square root of -1, we're going to let that to be I, or in other words, I squared is going to equal -1. So the first thing we need to do, we need to decide how we're going to define addition, subtraction, multiplication and division on these imaginary numbers, just our everyday operations. Well, we're just going to do it in a very natural way. So for example, if I have 3i plus 5i, it's pretty much like adding variables or adding like terms. So naturally this is just going to be 8i. 4i minus 10i, Again, it's the same thing really. So naturally you have 4 lots of I, you're subtracting 10 lots of I. Just like when we work with variables, it's going to be negative 6i. Okay, 2i times 7i to the 4. Well, we know 2 times 7 is 14. Now you got I times I to the 4, so you can think of this guy as being I to the power of 1. And so I'm multiplying two things with the same base, and so I add their powers. So I get I to the power of 5. Now the thing to keep in mind is that I is the square root of negative 1, or more precisely, I squared is equal to negative 1. So I can simplify down this I to the power of 5. So I know I squared is negative 1. So I to the power of 4, well that's just I squared squared, which is negative 1 all squared, which is just 1. So I to the 5, which is just I times I to the 4, becomes I times 1, which is I, and therefore I can simplify this down to 14i. So you can see that working with imaginary numbers, it's just like the arithmetic works exactly the same way. The only thing you need to be mindful of is that whenever you get an I squared in your calculations, you've got to replace that with negative 1. So for the last one, for instance, if you got 6i cubed divided by 2i, well, you know 6 divided by 2 is 3. Now I cubed divided by I, so you're dividing two things with the same base. So you subtract their powers, you get I squared, but you know I squared is negative 1. So this becomes minus 3. So operating with these imaginary numbers is quite straightforward. Now you might be thinking, well, that's all well and good, but what if you have something like 3 plus 5i? What would you do there? Well, the answer to that is really you can't do much, because 3 plus 5i are different things altogether. It's like saying adding apples and oranges, or in terms of variables, like adding x and y. You can't simplify x plus y, right? Likewise, you can't simplify 3 plus 5i. Now, so 3 plus 5i, that, or more generally something of the form x plus iy, this is what we call a complex number. So when you have a real number, in this case x, plus I times another real number, in this case y, we call that a complex number. So you can see complex numbers, they have a real part. So for example, with 3 plus 5i, the real part is 3, and we write it like this. So this is the notation that we use. We just put a RE out the front, so this reads as the real part of 3 plus 5i is 3. Likewise, this reads that the imaginary part of 3 plus 5i is 5, because we know the imaginary part is 5i, and so the imaginary part, we define that to be 5. Now what we can do, we can plot complex numbers on the xy plane, because you may be wondering, how do we actually visualize these complex numbers? Well, we can take the xy plane that we already have and that we use all the time, and what we can do, we can use the x-axis. We can now think of the x-axis as representing the real numbers, the numbers we use every day, but think of the y-axis as representing the imaginary numbers, right? And when you think of the xy plane in this way, we call that the Argand diagram, or the complex plane as well, is also what it's called. So just to give you an example of how this works, I've got a few complex numbers here, and I want to plot them on the Argand diagram. So it's very simple. So first let me draw my axis. Okay. So like I said, I'm just using my xy plane. But what I'm doing is I'm thinking of the horizontal axis as representing the real numbers. So reals. Yeah? And here I'm thinking of the vertical axis as representing the imaginary numbers. Okay, so usually you don't quite write it like this. Instead of writing reals, you might just write RE, and instead of imaginary you write IM. But this is just as an introduction. So now if you want to plot 1 plus 2i, So let me label some points here. So obviously this is the origin. So let's say this is 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, okay? Those are my real numbers. Now, vertically I've got my imaginary numbers. So let's say this is I, 2i, 3i, 4i, etc. And going down, minus I, minus 2i, minus 3i, etc. So now, for instance, if I want 1 plus 2i, well, the real part is 1, so I come up from here, and the imaginary part, well, the imaginary part is 2, but I want 2i, right? So it'll be this point. So on the Argand diagram, this point corresponds to 1 plus 2i. So fairly straightforward. If I want minus 2 plus 3i, so now on the real axis I want minus 2, on the imaginary axis I want 3i, and so this point where they meet corresponds to the complex number minus 2 plus 3i. Okay? Something like minus 3, right? Well, minus 3 is just the real number. So it sits on the x-axis, so it's right here. And in part D, you've got minus 2i, so that's a purely imaginary number. And that just sits on the imaginary axis, so it's down here. So that's pretty much how you plot complex numbers on the Argand diagram. Like I say, very intuitive when you use the xy plane.